Ugo Dal Lago from Bologna, and my former PhD supervisor, Georg Moser from Innsbruck. So I think in this community I don't need to motivate or tell you why functional programming matters. I think everybody of you knows. Rather, I should say a big thank you to the community here, because I have the feeling that I really profit a lot from your work. I almost daily program, so do functional programming. And the nice thing for me is that functional programming really gives you very nice abstractions to rapidly develop a software that once you manage to get it compiled, it really works. I mean, of course, you write your software, it compiles, it's fine, but then at the end of the day, which is also often, which you can also observe when you look at the community, you have to go back to your source code. Maybe you need to do some profiling and then attack the places where your software runs slow. Now, the great vision that we have is actually to let the compiler tell you where your software is running slow, or give you at least some information about resource usage. So this is our great vision. It's still a vision, but this vision is coming closer, since over the last years, in particular in the rewriting community, there have been lots of efforts to make this vision really become true. And as a result of this one, quite recently, you also see the development of a lot of tools that tackle this specific problem. So these tools all take as input some program written in some language, and then give you some resource information about this program. Let me make some advertisement here. In Innsbruck, I was together with Georg Moser and a colleague of mine, Andreas Schnabel, also developing such a complexity analyzer. What this one is doing is it takes as input the term rewrite system that you can just conceive as a first-order functional program. So you have a set of equations, and reduction happens by applying these equations from left to right. So you provide our tool TCT, the Tyrolean complexity tool, with such a term rewrite system, and then it applies a lot of sophisticated techniques and gives you an asymptotic upper bound of the runtime complexity of this rewrite system. What's runtime complexity? Essentially, we measure the number of redactions that this one is doing. So it's in development since 2008, and it has really reached a state where it can prove something about the complexity of non-trivial programs. So we have more than 20 techniques, and maybe one of the nice things is also that this tool is putting a lot of efforts into decomposing the problem into various smaller sub-problems, solving these sub-problems, and then combining the bound that it derives on these sub-problems. So to put it short, we put a lot of effort also on modularity there. So this is very nice and encouraging, but the bad news is that TCT is still not practical. Why is it not practical? Because foremost, TCT cannot deal with certain properties of programs that are really essential and in use every day. So in particular, when it comes to functional programming, TCT is currently restricted to first-order systems, which is pretty boring. So in order to change this one way to do this one is now to look into techniques and integrate techniques in our tool that can deal also with higher order functions. Such techniques already exist. I mean, just in the previous talk, Norman was talking about cost functions. There are also various type systems that deal with complexity analysis of higher order programs. The drawback here is that if we want to use these techniques in an automatic complexity tool such as TCT, then there is still work to be done. Like we have heard previously, mostly automation is still an issue. Also expressivity is an issue. Now, another way to overcome this problem is to sort of see a first-order prover like DCD, just like a black box that takes a first-order system as an input, gives you a complexity certificate, and before that, you just translate the program that you're really interested in, this higher order functional program, for instance, into this format understood by this black box. And of course, if you want to follow this transformational approach, there are some constraints that need to be satisfied. So first of all, maybe the most important thing is, once you get in this pipeline a complexity certificate, then really you want to translate this certificate back to the higher order program that you're interested in. So in particular, this means that this box marked with the question mark should not operate as an optimizer, right? You don't want to make the program that you're interested in more efficient. Why? Because this tool should actually tell you where are the inefficiencies. Ideally, you also want to have that the inverse direction holds. So you don't want to that this question mark here, this translation from higher order to first order, blows up the complexity of your program too much. And then, of course, what's also very important is that the thing that comes out, this first order program or first order rewrite system, should really be amendable to an automatic analysis. So you don't want to produce any garbage that the first order prover cannot understand. Now, the question is, how do we achieve such a transformation? And the obvious candidate is Reynolds defunctionalization, right? So it's quite well known, I think more than 30 or 40 years. So I don't want to go into details here. I just want to demonstrate you how this one works on a small example. This example is computing the reversal of a list. It's taken from a paper by Olivier Danvy on defunctionalization. And it's reversing this list in quite an interesting way. So it's a higher order program, and the interesting fact here is that it's not merely passing functions around, but really this walk function here, which is defined by recursion, the list that we supply, first constructs a function that then is really doing the job, provided we supply this function with the empty list. So now, how can we formulate defunctionalization in such a way that we get out such a first-order term rewrite system? Well, the idea here is quite simple. Whenever you encounter a function, you encode this function as a first-order data structure, or more precise, actually what you do is here you encode closures as a first-order data structure, and then you just define a global apply function here written in infix notation, this blue at, that tells you how do we reduce the function that is encoded. So for instance, here in this first line, you see the definition of this apply function for this for the composition function. So in the closure, we store the arguments f and g that are captured here by this composition function, and then we just tell how do we evaluate further such a function closure in the most obvious way. And then you just carry out this construction for each abstraction that you can encounter in the program, and you replace every function application by a call to this binary apply function. So far, so good. If we do this one correctly, which is not so difficult, then on the one hand, we really get out a system that is understood by current first-order provers. But on the other hand, the complexity of the defunctionalized program is related in a step-by-step manner to the complexity of your higher order program. So that's very nice. But unfortunately, then if you provide such a defunctionalized program to a first order prover, then you will soonish realize that in almost all cases, these first order provers just fail to tell you anything about the complexity of this program. And now, what's the problem here? Well, the problem here is that, well, you write this program down sort of in a first order syntax, but in spirit it's still a higher order program. So you see this best if you look at this encoding of the composition rule. You still sort of pass functions around and you apply them. So in terms of what a first order prover is doing with this one, it turned out that it's very difficult to analyze one global apply function, which in essence is just interpreter specialized to the program that you're considering. In particular, what's very bad is that also, well, as I mentioned before, TCD tries to divide the input into smaller problems, and to this extent, it computes a call graph, and this, modularity technique is actually driven by such a call graph, but the approximations used in such a tool are just too weak, and what they see here is essentially always one big SCC that cannot be further split into smaller problems that can be analyzed separately. So maybe our main contribution was then the observation, okay, defunctionalization is not enough. We just need to apply a handful of quite simple program transformation techniques to make this overall approach, this pipeline, feasible. And in our paper, we describe on the one hand the program transformations that we use, but on the other hand, we also describe our reference implementation that we call HOCA, which is taking this position, so which takes as an input a higher order functional program and produces such a first order TIS that can be effectively analyzed by a first order tool. And of course, all transformations that are involved in this big red box are shown to be complexity reflecting, if not preserving. So I don't want to go too much into details here. Essentially, what HOCA employs are 4 different transformations. The first 2 ones, inlining and dead code elimination, I think you're familiar with this one already. I don't want to go into details here. As it turned out, inlining greatly facilitates the analysis with first order provers, and dead code elimination also plays a major role in our tool. But I don't want to speak too much about this one. I want to speak more about the 2 transformations, namely instantiation and uncurrying, that really then perform this job of transforming this defunctionalized program that is in spirit still higher order to a true first order rewrite system. So the role of instantiation is to get rid of higher order variables as a first step. And as a second step, if we got rid of these higher order variables, then we can use uncurrying to finally eliminate this global apply function, which is so difficult to analyze. So what's the intuition behind instantiation? It's actually very simple. If we consider again this critical rule that defines the composition rule, if you look at the reduction of your rewrite system, it's quite easy to see, at least by hand, that these higher order variables f and g are instantiated by a very limited set of encodings of functions. Namely, in this case, f can either be closure 2 or closure 1 of f and g is always of the form closure 3 of x. So now, once you found out that f is always of this shape, then nothing prevents you from taking this rule and instantiating it to these specific patterns. Which means that, so what's the overall effect? First, we had a rule that uses higher order variables, but now once we have these instantiations, we really know which functions are applied in which positions. Of course, we need to be a bit careful that this instantiation is really sufficient. So in other words, we must not forget any case here in the estimation of these binders. Now, once you have such a system where all the higher order variables are eliminated, then it's actually very easy to replace all your applications by a new function symbol, fun of n, that is just, well, this is the usual idea of uncurrying. Instead of applying n functions separately, you just use one function that computes the result of applying these n arguments at once. And this idea we then just extend to applicative rewrite, to such rewrite systems in the obvious way. So for instance, these two previous rules, here we apply CL1 to one argument, we introduce a new uncurried definition here, and yeah, I think that's quite self-explanatory. The only thing is you need to be a bit careful that all these uncurried functions, that you really define all these uncurried functions. So this is very good, because using these four very simple transformations then, our tool can, our tool comes up with this reduced system of the defunctionalized version, which is very close actually to what the original program is doing. So if you look at this recursive structure here, actually it's very simple. You essentially have two recursions going on. The first recursion here with rule 3 and 4, the definition of walk, is building up this closure. It's constructing this function that is doing the job of reversing the list. And the rules 1 and 2 then tell how do you evaluate this constructed function. So this program, I mean, it's very obvious to see now from this first order program what's going on really in the higher order program. And indeed, this system is now in a shape that tools like TCT can infer. Optimal, even in this case, an optimal ground for this rewrite system. Of course, that might seem all very easy, but we had we faced some challenges. For instance, inlining is not cost neutral. In fact, it's usually optimization technique, which is harmful in our context. So what we introduced was a sufficient condition that tells you when you're allowed to inline without optimizing the program too much. Then again, inlining may blow up program sizes or diverge. Then instantiation is also very tricky because, I mean, your software needs to decide how do you instantiate the higher order functions. And for that, which I guess is a novelty, we use a control flow analysis. Another issue is how to spot dead code. And at the end of the day, of course, you have a bunch of transformations, and you need to, well, apply them in a way that it's really effective and efficient. So I want to jump over these slides. I directly want to go to the conclusion. So what I want that you take with you from today is that complexity analysis of higher order programs can really be effectively reduced to the first order case. That's also reflected, I think, in our experimental results. I think this approach has several advantages. Maybe the biggest advantage is that we can really harness state-of-the-art first-order provers and also profit from further development. Maybe a big disadvantage here is, of course, that inherently this approach is not modular. But on the other hand, I think our task is again inherently not modular. So maybe this is the price we need to pay. Yes, of course. First of all, instantiation can blow up program code, of course. But I think that just happens in corner cases. And of course, with inlining, you need to be very careful where you perform inlining and to which extent do you consider recursive functions and so on. So, and our solution to this problem is morally to define a metric on program that takes program sizes into account in order to avoid this blow-up problem.